Alright, so this video is meant to help out those who might have missed the day that we walked through assignment number 1 together. There really wasn't a whole lot going on with assignment number 1. There's a couple different ways we could apply some of these problems that we're dealing with in assignment number 1, but for the most part, what we've got going on is a few applications of Newton's second law, but it's really just Newton's second law, F equals ma. Let me modify this to be the version of it with the work being shown so that I can keep my original. Anyways, so in this particular case, that's all we're dealing with, right? I've already made a video and I've got those resources available to you guys if you need them for help with remembering what his 3 laws were, how they relate to one another. I'll happily go over any of that in class or in person, via email, whatever. But primarily what we're dealing with here is going to be just the equation F equals ma, right? His second law states that if an object accelerates, that there was a force that caused it. Up to this point, we've just talked about distance and time and speed and velocity, well, those are the same, and acceleration and how things move. Now we're getting into the why, and that's what Newton basically laid the mathematical foundation and framework for, was why things move. He did a lot of work, and what we can basically boil most of that work down to, at least for this portion of the class, is the equation F equals ma. So if in number 1 we're looking to calculate an amount of force, that's what they're asking you to solve for. Again, a force is going to be measured in a unit called a Newton. I'll talk about that briefly in a second. Knowing that Amanda and her bicycle have a mass of 80 kilograms and are accelerating at a rate of 1.85 meters per second squared. These are things that are provided to us, right? Kilograms tell me it's a mass. Meters per second squared tell me it was an acceleration. And we're simply going to plug it into F equals ma, where our force is equal to our 80 kilogram mass. We have 1.85 meters per second squared as our acceleration, and we are going to wind up with a force of approximately 148. Now the units for this force traditionally, there for a while, and even Newton himself described them as a kilogram meter per second squared. My point behind writing this and including this is that I'll never do it again, number 1, but number 2, all of these more complicated units that we're coming up with, be it newtons or watts or joules or amperes or whatever, that we're going to talk about throughout the course of this unit, or this school year, they all come from these fundamental measurements. They come from mass, they come from distance, they come from time, they come from temperature, they come from, the count of things, being maybe moles or some of the other ones. You had lumens and charge, right? Charge is going to be measured in coulombs. So all of these things come together to give you these more complicated measurements we could make, but basically it boils down to us being lazy. And instead of wanting to say kilogram meter per second squared every single time, we decided to, altruistically make it look like we're naming it after him, which we are. But we call these units for forces a Newton because it's easier to say than a kilogram meter per second squared every time we want to talk about these problems. Number 2, we've got ourselves this little primate guy. He's applying a force of 255 newtons to the tree. He's going to be accelerating at 4.2 meters per second squared, and they ask you to solve for its mass. Mass is always going to be measured in kilograms, not grams. That'll pop up on the next worksheet. Just make sure you recall that. So it's still Newton's second law, F equals ma. That hasn't changed in any way, shape, or form. It's 255, and I'm going to write it out this way just to remind you guys where this comes from. The official unit for a Newton was a kilogram meter per second squared, and that's going to be equal to your mass multiplied by 4.2 meters per second squared. And you'll notice that since mass and 4.2 are being multiplied together, you divide both sides by 4.2. You're going to get yourself not only our value for mass being 61, I think it was like 60.8, but it's close enough, but you'll also notice your units of meters per second squared will completely cancel out. So a Newton divided by a meter per second squared is a kilogram, because the unit of a Newton was kilogram meter per second squared. So it's the only unit out of that whole amalgamation of many, many, many smaller units that survives. It's the one that makes it out of there. And that's why you'll often see me dividing a Newton by a meter per second squared, and I'll just write kilogram because we know where it came from. All right, we've got Roman in number 3, pushing a chair, applying some sort of force to it. The force he's applying is 50 newtons. His mass is going to be 15. Guys, it's the same equation. F equals ma. In this case, it's 50 newtons is equal to 15 kilograms multiplied by your acceleration, not added or subtracted. So we divide both sides by 15, and that acceleration is going to work out to be, 3.3, I think it was. Yeah, 3.3 meters per second squared. So that was the acceleration if only Roman was pushing on the chair in number 3. That's not the only case, and this is actually where we get to a big idea in all of this unit, all of physics really for the most part, but this unit. In this particular case, here's my chair. I don't draw actual things. My 7th grade art teacher is still disappointed in me, I'm sure. We have a force being applied by Roman of 50 newtons. I'm just going to leave his force being applied in the rightward direction. And then Sylvia comes along and applies an opposing force, a force in the opposite direction of Roman. So I'm going to try and draw her arrow just a little bit larger because she is applying just a little bit more force. And so Sylvia's force vector of 63 newtons is in the exact opposite direction. And this gets at the main idea. Normally, we would have just jumped right into F equals ma to calculate the acceleration, but then you're left with the question, am I going to apply Sylvia's force? Am I going to apply Roman's force? Do I just ignore one? Do I flip a coin? What do I do? And the short answer is that you have to include both, right? If you're pushing this chair and someone comes along and pushes in the opposite direction as you, at very least, it's going to slow you down. There's a possibility that it could bring the whole thing to a complete stop if you guys are pushing with the same amount of force, or in this case, because Sylvia is applying more force, Sylvia is going to actually wind up winning. So we've got to come back to this idea that was from the text, from the book, of a net force. And this idea is basically that if we want to find out what the overall interaction of all of these forces are, what the resulting combination of all of these forces are going to be, we have to add them all up. And so the net force is literally the sum of all forces acting on an object. And the sum of all forces acting on the object, it literally means that we just add them up. So my net force, this isn't really an equation, so you don't see it on the front of the packet. I don't think it deserves its own equation because it's going to change depending on every scenario that we ever look at. It's more of an idea, right? If you're going to have the sum of all forces, you just add up the forces that are present. And in this case, we've got 2 of them. We have Roman's force, and we're going to add that to Sylvia's force. But because direction is such a big idea in physics, we have to account for that direction by using positives and negatives. So we're literally adding a negative 63 to our positive 50. That is naturally going to give us a negative 13. That negative 13 Newton net force is then what we come down here and add to F equals ma. In fact, I want you to, on your equation card, not write F equals ma. It is not just one random arbitrary force that you have selected because you like that number better, right? I'm not going to pick 50 because it's an even number. I'm not going to pick 63 because it's the larger number. We have to find the net force. And it is that net force that causes an acceleration. That's going to be a big deal when we come back to what we're going to talk about. What problem was it? I think it's the last. Yeah, it's the last problem on this worksheet. Actually, that'll be the last thing I can talk about. So we're going to come back to this idea of net forces. From here, naturally, you're going to have your negative 13 newtons equal to still 15 kilograms. Just because she came along and started pushing on the couch too doesn't mean the couch got bigger or smaller. The couch is still the same mass. We still divide both sides by 15, and your acceleration is going to work out to be something significantly less. It's at the end of the worksheet, 0.867. So 0.88. I could round that too, but it does still need to be a negative, and it needs to be a negative because we described Sylvia's original direction as negative, and this is now accelerating in Sylvia's direction. That's one of the nice things about this unit is we can start applying that. We could have applied common sense to it before, but this gets a little bit easier to apply some of that common sense to, because obviously it should be in her direction. She's applying more force. She's going to be winning if this were tug of war. That's really all it was. Number 5 is a really good question. This is an example of some of the stuff you're going to see on your exam, right? I wrote the exam, so this is going to be something you're going to see on the exam. It's a combination of some of our old stuff and our new stuff, naturally. So Rich is driving his car at a speed of 22 meters per second. That is not a typo. I know that we have accelerations that we're dealing with in F equals ma, Newton's second law, but I intentionally gave you a car's velocity. I even wrote the word speed next to it to try and signal what that should have been. The next number that I come across is a measurement of time. It's 10 seconds. Then I see a mass of 1,200 kilograms, and I see that the car came to a stop, which tells me my final velocity is 0, which tells me I can go back and give that 22 meters per second the label of my initial velocity. From there, they ask how much force was needed to make this happen, right? Your car's coming to a stop. They want to know how much force the brakes had to apply to the road in order to get this whole thing to come to a stop. Now, the first equation that should come to mind when I ask you to calculate a force is F net equals ma. Now, the brakes in this particular case are going to be the only force we're dealing with, so that's our net force isn't anything extra that we have to do. But we still have to find out what that is, and it's going to require an acceleration. So one of the things I know I'll see on the exam, please don't be one of those people, is people will just arbitrarily take 22 and plug it in for your acceleration. You can't do that because 22 is a velocity. You can't plug 10 in for your acceleration. You can't plug 0 in for your acceleration. And you should not plug in negative 10 meters per second squared for gravity, because gravity is not causing Rich's car to come to a stop, right? It's not in free fall, so gravity is not the accelerating force here. What you can do and what you will do is come back to some of the older stuff that we had and be able to calculate your acceleration from the other pieces of information that were provided. Obviously, nothing we've talked about before Unit 5 is going to include a mass. So that mass, that 1,200 kilograms, will go right there in F equals ma. But if you want to find the acceleration here, it is your change in velocity divided by time. Be careful. A lot of you just write v over t. It is not one velocity divided by time. It is how your velocity changed. That may seem stupid right now because our final velocity was 0, and if we add in that detail of subtracting 0, well, then it's still just 22. Sure, but look at the order that they're going to be subtracted in. It's your final velocity minus your initial velocity every single time. And while you might have not noticed this step had you skipped it, once you write it out as 0 minus 22, it becomes very apparent that this acceleration should actually be a negative 2.2 meters per second squared. And that should make perfect sense if you think about what the Jeep is doing, what the car is doing. It's coming to a stop. And so this acceleration has got to be negative. It can't be anything other than negative. Every second it loses 2.2 meters per second worth of speed. It's got to be a negative acceleration. Once you get that negative acceleration, then you can come down here and plug it into F equals ma. All right, so it's 2 steps. Use the information provided to get acceleration, and then plug it into F equals ma. 2 steps that we've done plenty of, right? F equals ma really isn't that complicated of an equation, so we are going to be incorporating some of the old stuff that we did. While we might not incorporate a full-on projectile motion, horizontally launched projectile sort of thing, we are going to be incorporating some of the old ideas of speed in order to help us calculate accelerations. Negative 2.2 meters per second was my acceleration, and then this is going to give me a force of something negative. It was like 2,600, I think. Yeah, 2,640. 2,640 newtons. Again, it's got to be a negative force because it's a braking force. It's causing it to come to a stop. Now, number 6, it's the same idea as number 5. I'm going to get rid of it. It's not going to be something you're going to have to do. Really, you've got multiple options because I give you both the distance the mitt recoils and I give you the time that it took for that recoil and that object to come to a stop, in this case the baseball. You can use VF equals VI plus a t, like I did in the last problem for number 5. Because you've got a distance, you can use VF squared equals VI squared plus 2AD to get your acceleration. Or, quite honestly, because you know both time, distance, and your initial speed, you could honestly use d equals VIT plus 1/2 AT squared, if that's something that you want to do. All of those ideas are perfectly fine. It would be a very large acceleration, but I'm not going to give you any question on the test where it is where it has that many options at the beginning of the problem. It'll be significantly more straightforward, like number 5, where you had VI, VF, and T. No mention of distance was provided, so that was the only equation you could choose. It'll be very clear-cut on the exam. Number 7, this is our second major idea here. First and foremost, we're given a mass for this snowflake in kilograms. That is always going to represent a mass. And then I'm going to write down something that I'm going to write probably on at least 30 exams when it comes time to taking this test and me grading them. And that is that mass is not the same as weight. If you have to write this 100 times to commit it to memory, then please write it 100 times to commit it to memory. Mass and weight are not the same. We in America, I think it's just we in society in general, regardless of what country you're from, we use these two interchangeably all the time. If you look at the back of a semi-truck, it's got the mass measured in kilograms and the maximum weight measured in pounds, both labeled right next to each other on it. If you go into the fitness center at the school or your weight room or at the gym or at home, and you look at the 45-pound plates that might be there, they have 45 pounds written there and then 20-point-something kilograms on the same plate, right? You'll always have the mass in pounds, or the weight in pounds and the mass in kilograms on the same thing, and that kind of leads to the misconception that they're the same, and they're not. Weight, by definition, is a force, and I always write this every time I see the word weight. It is a force of gravity. Maybe I won't write out all of force of gravity, but I will write F with a subscript of a G, because that's how I represent my force of gravity. Capital F, because it's still a force, it's still measured in newtons, but the cause of that force is gravity. And because it's a force, we still use Newton's second law in order to calculate it. It's just we're being specific. And so it's going to be F with a subscript of a G multiplied by not just any acceleration, but the acceleration due to gravity. It's always going to be -10. So anytime you see little g from here on out, actually in the class, just until the end of the year, until you graduate, it's going to be -10. That's what I use for gravity from here on out, because we might have horizontal accelerations and things too that are still on Earth, and we have to take into account the weight of the vehicle. So if you wanted to calculate it, it is the same sort of process we've always had. It's 0.0002 kilograms multiplied by acceleration due to gravity is -10 meters per second squared. Multiply those two values together, your weight works out to be a -0.002 newtons. Yes, it should be negative. That seems ridiculous, I know, but it is a vector. It includes direction. You've never stepped on a scale and had it read a negative weight. I know that. That's because the scale, actually, that you're standing on doesn't measure your weight, your downward force of gravity. What it does measure is it measures how much force the scale has to apply back up at you to counteract that force of gravity acting on you. And so it's actually reporting your normal force. And that's why we don't see negatives on the scales, at the doctor's office or in our bathroom at home or whatever. I mean, that part of it isn't going to be a test question, but you do need to include direction. Weight should always be negative, period. Last but not least on this page, and this gets back to actually what we talked about in number 4. Michelle is pushing a shopping cart, and she's applying a force of 20 newtons. So I'm going to label that as F with a subscript of an A. If you're curious as to why I put these subscripts on these letters, please go check out the first set of notes, Unit 5, N1 for Note Set 1. That video gives you a walkthrough not only of net force, but also how I label these things and why I label them the way that I do. So if you need that reminder, go check that out. We've got 20 newtons of applied force that Michelle is giving this cart. And then you've got friction. The force of friction acts in 20 newtons. This is going to be a test question. It's also one of the questions on assignment number 2. One of the first things you'll encounter on assignment number 2. Friction acts in only one direction. One direction and one direction alone. And that one direction is not north, south, east, west, left, right, up, or down. That one direction is always opposite the motion or attempted motion of the object. And this was talked about in those earlier sets of notes, right? So that force of friction is always going to be in the opposite direction that you are trying to move the thing or that the thing is moving. And so in this case, if you wanted to do that calculation for net force that we had done from before, you can, right? Your net force is going to be the force applied plus the force of friction. Your net force, clean that up, make it look a little more like a subscript as opposed to chicken scratch, sorry, is going to be 20 plus a negative 20, because we have to include direction, right? The force of friction I made negative. You could make whichever one of them you want to be negative. It doesn't matter, because your net force is going to come out to be 0. You have no net force. She's pushing with as much force as friction is also applying, and so they cancel each other out. That's the big idea. Now let's come down here to our second law. F net is equal to ma. If your net force acting on the cart was 0, then your acceleration should also be 0. It doesn't matter what your mass is. If your net force is 0 on the object, that mass could be 10 kilograms, 100 kilograms, 1,000 kilograms. It doesn't matter. Acceleration is still going to be 0. Now, this leads to a question that a lot of us are going to miss on the exam. This does not mean, and this is what everyone initially thinks, if I were to ask you, and take a second to think about it when I ask, if the cart has no net force acting on it, what is the cart doing? And the first thing that usually comes to people's minds is it's not moving. And that's only half true, right? It can be moving. If this cart had an initial velocity of 5 meters per second, what Newton's first law really says isn't that things that aren't moving are going to remain not moving in perpetuity, right, for forever, unless an outside net force comes along and nudges it. What it's also saying is that any object that is already moving will continue moving at that speed forever until an outside unbalanced net force comes along. So all a 0 net force means, 0 net force tells you that there is 0 acceleration, and then that tells you that the object doesn't change its motion. Doesn't change motion. Because that's all acceleration is. Remember, acceleration doesn't mean something is moving. Acceleration just means that something is changing its speed. And so if it changes that speed, it speeds up, slows down, whatever, then it could be applied either to moving things or to things that aren't moving. It doesn't matter. And that's going to be one of the big ideas, right? Newton's first law is an object in motion will stay in motion unless acted upon by a net force, and an object at rest will stay at rest unless acted upon by a net force. His second law then obviously calculates the relationship between those two things. But that was about it. That was assignment number 1.